Welcome back to The Deep Dive, your regular update on what's actually moving the needle in machine learning research.
Great to be here.
Today, we're tackling something, well, foundational in generative AI. It's this challenge of making audio and video not just exist together, but actually be generated together seamlessly.
Right, avoiding that whole awkward phase of trying to stitch them together after the fact.
Exactly. So we're diving into a paper that really pushes this forward. OVI. Twin backbone cross-modal fusion for audio-video generation.
This is out of character AI and Yale University.
And it's a significant piece of work for anyone needing the quick takeaway, maybe for that short-form clip. Here's the essence in about a minute.
Let's do it, the 1-minute rundown.
Okay, so OVI's core mission, it's about ditching those really complex, often brittle, multi-stage pipelines. You know, the whole text-to-video, then text-to-audio thing.
Yeah, T2V, then T2A or A2V.
Yeah.
It gets messy.
Precisely. OVI wants to model audio and video as one single generative process, unified from the start.
And the architecture enabling that. That's the twin backbone. It's this massive, symmetric, 11 billion parameter setup. Think two identical latent diffusion transformers DITs running side by side. One for video, one for audio.
Identical. Okay, interesting. And how do they talk to each other?
That's the fusion magic. They use blockwise, bidirectional cross-modal fusion, and crucially, it's inserted into every single transformer block.
Every block. So continuous interaction.
Continuous, yeah. Constant exchange of semantics and critically timing information between the audio and video streams.
Which leads to the big payoff, synchronization,
Right.
Things like lip sync, sound effects matching the action.
Exactly. It happens intrinsically. It emerges directly from that deep fusion, plus something called scaled ropey embeddings. We'll get into that. The point is no need for hacky post-hoc fixes or masks.
And the output.
Pretty impressive for open source. We're talking high-quality, synchronized 5-second clips, 720p resolution, 24 frames per second. And human evaluations show people strongly prefer it over previous open attempts.
Okay, that's a solid minute. It really sets the stage. Because as anyone working with video or film knows, you can't just treat audio and video as separate things you glue together later.
You really can. Cinematic content, even just good quality video, demands that joint composition. Speech absolutely has to match lip movements.
Footsteps need to match the walk cycle. Music cues need to hit with visual changes.
Right. And most open source stuff before this, fixed one modality, maybe generated the video first and then tried to synthesize the audio to match, or vice versa.
Which really limits what you can do, right? It often ends up being useful only for things like maybe animating a still headshot to talk.
Or you end up relying on those really fragile alignment steps afterwards, which often don't quite work perfectly.
And the paper makes a good point, this idea of truly unified one-pass AV generation, especially at scale. It's been kind of a black box in the open literature.
Yeah, the big system everyone points to is Google's VO3, but that's totally closed source. We don't actually know how it works under the hood. So OVI is kind of defining an open approach here.
So let's recap OVI's main contributions, the pillars of this work. You mentioned the data pipeline.
Right. First, a massive AV data pipeline. Millions of videos, but with super strict filtering for synchronization. That's key. And they use a combined prompt conditioning scheme. A single T5 pass handles both visual and audio descriptions.
Okay, the single prompt is interesting. We'll definitely circle back to why that unified input works. What's next?
Second, well, it's the core architecture we touched on, that 11 billion parameter symmetric twin backbone, with the blockwise bidirectional fusion and the scaled rho P for timing.
Got it. The hardware and the interaction mechanism.
Third, the fact that this enables an end-to-end one-stage generation process. It achieves that strong synchronization without needing heuristics or fixes after the fact.
And fourth,
a scalable training recipe. They figured out how to train this beast effectively, involving audio pre-training, then the fusion fine-tuning, to get those high-quality synchronized results.
Okay, let's dig into that architecture. An 11 billion parameter symmetric backbone. That's a lot of parameters. Why the insistence on symmetry? Why make the audio and video backbones identical? Wouldn't a smaller audio model have been maybe more efficient?
That's a great question. It seems counterintuitive maybe, but the symmetry is actually designed to reduce friction. See, when you have different architectures for different modalities, you usually need these intermediate projection layers.
Right, to map the latent space of one modality onto the other.
Exactly. And those projection layers can be lossy. They can introduce bottlenecks. By making the backbones architecturally identical, same model, dimension, 30 blocks, 24 heads, everything, they just eliminate the need for those projections.
Ah, so the latent spaces are already compatible, structurally. When they meet in the fusion layer, the attention mechanisms just work without needing that translation step.
Precisely. It simplifies the crucial cross-attention process. And that process happens in these fusion blocks. This is really the heart of it.
Yeah.
Blockwise, bidirectional cross-modal attention in every single transformer block.
So constantly, the audio stream is looking at the video stream, and the video stream is looking back at the audio. A continuous dialogue.
A continuous dialogue, yeah. It grounds the audio in what's happening visually, and it informs the visuals based on the sound. It's properly intertwined.
And guiding this whole process is that single instruction set you mentioned, the frozen T5 encoder, taking one prompt that describes both the visuals and the audio.
Yes, they concatenate the video caption and a rich audio description into one input for T5. This forces the model to interpret the instruction as a single command for a unified audiovisual output.
Okay, but here's a challenge that immediately jumps out. Time. How do they handle the huge difference in temporal resolution? You said 5 seconds is 31 video frames, but how many audio tokens?
It's 157 audio tokens for their 16 kilohertz VAE setup. So yeah, way more granular on the audio side, over 5 times the resolution.
Right. So if you're generating someone speaking, how does the model know that, say, audio tokens 70 through 85 correspond exactly to the mouth movements happening in video frames 15 through 18? Standard attention might be too fuzzy for that precision.
This is where the scale ROPE comes in. Rotary positional embeddings. They apply ROPE to both the audio and video latents to give them a sense of time. But, and this is the clever bit, they scale the frequencies used for the audio ROPE.
Scale them how?
They scale them down by the ratio of the resolutions. So by 31 divided by 157, which is about 1/197. This effectively makes the audio sense of time coarser, matching the video's temporal resolution for the purpose of cross-modal attention.
Ah, I see. And does it work? Can you see the effect?
Oh yeah, they show visualizations of the cross-modal attention maps. Without scaling, the map showing which audio token attends to which video frame looks. Well, messy, kind of scattered.
But with the scaling.
With scaling, you get this really sharp, clear diagonal line in the attention matrix. It means audio token X is strongly attending to video frame Y, right where you'd expect it temporally. It provides that crisp correspondence needed for things like lip sync.
That's elegant. It's achieving temporal alignment mathematically within the embedding space rather than needing a separate alignment loss or mechanism.
Exactly. It bakes the alignment right into the attention process via ROPE scaling.
Okay, so that's the architecture. But we know models are nothing without data. You mentioned a massive, heavily filtered data set. Let's talk about that pipeline.
Right. Data hygiene was clearly paramount here. They curated 2 main data sets. One was a paired audio-video corpus. That's for the main fusion training. The other was a huge audio-only corpus.
What was the audio-only data for?
That was for pre-training the audio backbone, getting it really good at generating all sorts of sound speed, sound effects from data sets like VGG sound and AudioSet, building a strong foundation before even thinking about fusion.
Makes sense. And the paired AV data, what about the filtering? You said it was strict.
Extremely strict. First, the basics. They chopped videos into 5-second clips, 121 frames at 24 FPs, filtered for high resolution, made sure there was actual motion using optical flow scores, even used a static predictor.
Okay, quality control. But the big one is sync, right?
Absolutely. This is where they use SyncNet, a well-known model for detecting audio-visual synchronization, especially for speech. They adapted it to run on millions of videos.
And the criteria for keeping a clip.
Super tight. The detected offset between audio and video had to be tiny 3 frames or less, absolute value. And the SyncNet confidence score had to be high, over 1.5.
Wow. Why be so ruthless? I mean, for the engineers listening, what happens if you let slightly misaligned data slip through, say, a clip that's off by maybe 6 or 7 frames?
Well, you're essentially feeding the model contradictory information. If sometimes the sound for ooh lines up with the right mouth shape, sometimes it lines up with the mouth shape for E, the model gets confused. It struggles to learn a reliable connection.
It averages out the signal into noise.
Exactly.
Yeah.
That strict filtering is probably why their intrinsic synchronization works so well later. They ensure the training data provided consistent, reliable cues for the model to learn from.
And the captions had to support this too, right? You mentioned they were quite detailed.
Very detailed. They used a multimodal large language model, an MLM, to generate verbose descriptions. It described visual events, but it also interleaved the actual transcribed speech within special tags, like S for start and E for end.
Ah, so the transcript is right there in the caption.
Right there. And then separately, within tags like AUDD cap, it included a rich description of other sounds, music, effects, ambiance. This gives that single T5 encoder everything it needs to understand the full AV scene.
Okay, clean data, smart architecture. How did they actually train this thing? You mentioned 2 stages.
Yep, a 2-stage process.
What?
Stage 1 was all about the audio. They called it OVI AUD pre-training. They took that audio-only backbone, remember, identical architecture to the video one, and trained it from scratch on hundreds of thousands of hours of audio data.
Just making a really solid text-audio and text-to-speech model first.
Exactly. Using a 1D VAE for the audio representation and optimizing a flow matching objective. This established a strong foundation.
Then stage 2, the fusion.
Right. Now they bring in the pre-trained video backbone. They initialize that from 2.2, a 5B parameter model. They put the 2 backbones together with the fusion layers and fine-tune them on the paired filtered AV data.
Now, fine-tuning an 11 billion parameter model, especially with cross-modal stuff, that sounds like it could easily go wrong. How did they prevent, say, catastrophic forgetting, where the model learns the fusion but messes up its original video or audio generation abilities?
The point, they use a smart trick,
Yeah.
parameter freezing. They didn't fine-tune everything. They specifically froze the feed-forward networks, FFNs, in the transformer blocks.
Okay, so what was trainable?
Only the attention modules, both the self-attention within each modality and, crucially, the cross-modal attention layers in the fusion blocks. That worked out to about 5.7 billion trainable parameters out of the total 11 billion.
So they focused the learning budget specifically on the parts responsible for relating the modalities and learning those synchronization cues, while preserving the core representational power learned during pre-training.
Exactly. It's a strategic way to manage the complexity and prevent the model from destroying its foundations.
And the loss function. How did they balance optimizing for good video versus good audio?
They used a weighted sum of the flow matching objectives for each modality, but they gave video a significantly higher weight. 85% of the loss came from the video objective, and only 15% from the audio.
85-15. Why prioritize video so heavily?
The thinking seems to be that the visual stream provides the primary spatial and temporal structure. You need really solid, high-fidelity video generation first.
Because the audio needs something stable and accurate to synchronize to.
Precisely. If the video generation is shaky or inconsistent, the cross-modal fusion doesn't have a reliable anchor. Getting the visuals right provides the necessary ground truth for the audio alignment cues to latch onto effectively.
That makes sense. So all this effort, the symmetric design, the strict data filtering, the careful training strategy, did it pay off in the results?
It really seems like it did.
Yeah.
They ran blind pairwise preference studies, comparing OVI against other open source models like JavaSDIT and Universe 1 on a benchmark called VerseBench.
And the outcome?
OVI came out clearly ahead, consistently preferred across different metrics, and the margins weren't small.
Give us some numbers. What stood out?
Okay, for example, when compared to JavaSDIT, users preferred OVI for video quality 90.7% of the time. That's huge.
Wow. And what about the key thing, the synchronization?
Even stronger in a way. For audio-visual sync, OVI was preferred over JavaSDIT almost 80% of the time, 79.3%.
Okay, nearly 80% preference on sync. That's not just incremental improvement. That suggests the unified approach is fundamentally better at solving the synchronicity problem compared to trying to stitch things together.
It really points that way. And interestingly, that foundational audio model, OVI AUD, which they pre-trained, it holds its own even when evaluated purely on text-to-audio or text-to-speech tasks.
So it didn't sacrifice unimodal quality to enable the fusion?
Apparently not significantly. It achieved competitive scores, like a low word error rates for speech and good CLAP scores for audio quality. This is important because real videos need both good speech and good sound effects, and the model seems capable of both.
And remember that single combined T5 prompt. Did they test if that was actually better than using separate prompts or encoders?
They did. An ablation study confirmed it. Their initial attempts might have involved, say, separate encoders for visual descriptions versus audio descriptions, maybe thinking it would prevent interference.
But it didn't work as well.
It actually performed worse. Switching to that single T5 embedding, fed with the combined prompt, significantly boosted audio fidelity and alignment metrics like IS and CLAP scores. It seems unifying the instruction signal helps the model generate a more coherent, unified output.
Simpler is sometimes better, even in complex models.
It appears so in this case. It streamlines the cross-modal modeling.
Now, the ultimate proof maybe is visual. You mentioned the attention maps earlier. The aha moment.
Right. Those visualizations are quite compelling. They show heat maps of where the audio tokens are focusing their attention within the generated video frames.
And what do they show?
When the model is generating speech, the attention converges really tightly, precisely on the speaker's mouth area, frame after frame.
Okay, that's strong evidence for learned lip sync. What about other sounds?
Same thing. If it's generating, say, an animal sound, the attention map highlights the relevant part of the animal's body. It confirms the model isn't just guessing, it's genuinely learning these deep spatial temporal relationships between sound and visuals directly thanks to that blockwise fusion.
It really validates the whole architectural approach. Okay, so OVI represents a big step forward, especially for open source AV generation. But like all research, it surely has limitations. Where does it fall short? What's next?
Definitely. The authors are upfront about the current boundaries. First off, duration. Right now, it's limited to these short 5-second clips.
Right. No long-form narratives, no scene changes, no real story consistency over time.
Exactly. Scaling up the duration while maintaining coherence is probably the biggest immediate challenge.
What else?
Efficiency is another one. That huge 11 billion parameter symmetric design, plus the dense fusion in every block. It takes a fair bit of compute time for each sampling step, especially with classifier-free guidance adding another forward pass. It's not exactly real time yet.
Understandable. And any constraints on the output quality itself?
The main one mentioned is audio fidelity. Because they use a 1D VAE operating at 16 kilohertz for the audio latence, it inherently limits the bandwidth.
So really high-frequency sounds, subtle spatial audio cues, maybe complex music, those might get flattened a bit.
Yeah, that's the trade-off with the current audio representation. Future work could definitely explore higher bandwidth audio VAEs or different latent representations to push that fidelity further.
Okay, so duration, efficiency, and audio bandwidth are key areas for future work. But stepping back, what's the big picture impact of OVI?
I think it provides a really strong practical template. The twin backbone architecture with that deep blockwise fusion. It's shown to be a scalable and effective way to achieve unified audio-video generation. It significantly narrows the gap between open source capabilities and those big closed frontier models like VO3.
It sets a new baseline and a new direction for open research in this area.
Absolutely. And that leads to a final thought, maybe something for our listeners to mull over, connecting OVI's success with its current limitations.
Go for it.
Well, OVI nails the synchronization, which is fantastic, but it's computationally heavy. We know there are techniques now like model distillation, things like DMD2, that are proving effective at drastically reducing the number of sampling steps needed for diffusion models without sacrificing much quality.
So the provocative thought is, could we apply something like DMD2 distillation to OVI?
Exactly. Could you take this high-quality, synchronized OVI model and distill it down, reduce those sampling steps significantly? If you could achieve that combination, OVI synchronization quality plus near real-time efficiency, that could unlock a whole host of new applications.
Bringing that level of unified AV generation to interactive or real-time scenarios, that is an interesting direction.
Something to think about.
Definitely. A great place to wrap up. This has been a fascinating look at OVI. If you want to explore the demos, see those attention maps, and dig into the architecture diagrams yourself, the project page link is in the show notes.
It's well worth checking out their video examples.
Absolutely. Thanks again for joining us on the Deep Dive. We'll catch you next time for another exploration of cutting-edge ML.